Okay guys, welcome to week 5 recap. I'm just going to jump right into it. The first thing that I have as a recap, or the things that I want to discuss, is to kind of go back to correlation. So, we've looked at some procedures that focus on comparisons of measured dependent variable across categories of an independent variable. Those types of procedures are generally applied to experimental designs for the purpose of group comparisons. Okay, like when we look at a t-test. Now we've kind of gone into looking at relationships, or to examine procedures for explanatory analysis. Now I remember someone asked about explanatory, and that's what that is. Okay, so when we look at correlation, we're getting into the aspect where we want to look at procedures for explanatory analysis or explanatory reasons, where the purpose of the research question is to evaluate the relationship between two measured variables. Now, where this is looking at, or I should say, this is where statistical tests of a group differences address certain questions like, is group A different from group B, or does a therapy cause a certain outcome? And that looks at, or it's measures of correlation. Okay, you're asking, what is the relationship between A and B, or does variable A increase with variable B? Now, the concept of correlation is a familiar one. We do talk about this often, and you will see it in a lot of research. Pairs of observations, X and Y, are examined to see if they tend to quote unquote go together. So like, for instance, we generally accept that taller people tend to weigh more than shorter people, or that children resemble their parents in intelligence, and that heart rate increases with physical activity. Okay, these variables are correlated in that the value of one variable, X, is associated with the value of another variable, Y. And with a strong correlation, you can infer something about the second value by knowing the first. Correlation can be applied to pair observations on two different variables, such as heart rate or level of activity, or to one variable measured on two occasions, like intelligence of a parent and a child. So correlation coefficients are used to quantitatively describe the strength and direction of a relationship between two variables. Okay? It's usually denoted as a lowercase r, and it provides an index that reflects a quantitative measure of the relationship between two variables. Sorry, I'm looking at this and I see I have a mistake. But what this should say is, for most applications, like I said, a lowercase r is used to represent a sample correlation coefficient. Correlation coefficients can take values, so this should say values, ranging from negative 1.0 for a perfect negative relationship to 0.0 for no correlation to plus 1.0 for a perfect positive relationship. The magnitude of the correlation coefficient indicates the strength of the association between an X and a Y. The closer the value is to plus minus 1.0, the stronger the association. Okay? And the sign of correlation coefficient indicates the direction of the relationship. In a positive relationship, X increases as Y increases, and X decreases as Y decreases. In a negative relationship, X increases as Y would decrease, and vice versa. In reality, because of random effects, we seldom see either a perfect or a zero correlation, so we typically encounter values of R that are still between 0.00 and plus and minus 1. These values are probably what you're going to see most of the time. And often it can be denoted or represented as where you'll see like a R equals 0.75 or R equals a negative 0.62. So here you see a small chart of what we use when we're looking at what is a strong or not a strong correlation. The value of the correlation coefficient is a measure of strength of association, like I said, between two variables. So there are no widely accepted criteria for defining strong versus moderate or moderate versus a weak association. So we use these guidelines to direct us. When we say 0.00 to 0.25, there's usually little or no relationship. 0.25 to 0.50, it's a fair relationship, and if we say 0.50 to 0.75, it's a moderate to good relationship, and anything above a 0.75 is considered a excellent relationship. The values that you see here, though, that they really should be used as like a strict cutoff. And they are affected by sample size, measurement error, and different types of variables that are being studied within whatever sample or population that you're looking at. So this is really to be used as like a starting point only. Okay, so let's look at relationship classification. So the coefficient R, which we talked about in this week's stat sheets, is a measure of a linear relationship only, okay? That means that the value of R reflects the true nature of a relationship only when scores vary in a linear fashion. And relationships can only either be linear or nonlinear. The closer the points are to a straight line, the higher the value that R will be. A coefficient R, like I said, is measured of a linear relationship only. And correlation coefficient is always subject to sampling error. So now let's talk a little bit more about correlation coefficients. So just like other sample statistics, the correlation coefficient is subject to sampling error, like I've stated already, and that is the observed correlation is considered one of an infinite number of possible correlations that could be obtained from a random sample of a population. Okay, so we can subject the correlation coefficient to a test of significance to determine if the observed value is a random effect or if it is a good estimate of the population correlation. The significance of a correlation coefficient does not mean that a correlation coefficient represents a strong relationship necessarily. Statistical significance only indicates that an observed value is unlikely to be the result of chance. And they are very sensitive to sample size, so that's something to consider. And statistical power can be relatively high even with smaller samples. But this is just something to think about. So let's move forward and talk about cutoff. But so the next topic that we're going to talk about is regression, because correlation, they're useful for describing strength in relationship, and that's where we fit in regression. So like I said, correlation statistics are useful for describing the relative strength of a relationship between two variables. But as a researcher, when we want to establish a relationship as a basis for prediction, we use a regression. The ability to predict outcomes and characteristics is necessary to making an effective clinical decision and for goal setting. It's also important for implications for efficiency and quality of patient care, and especially in situations where resources may be limited. Regression analysis will often provide us with we can use it as a powerful statistical approach for explaining and predicting quantifiable clinical outcomes. So if we were looking at functional assessments in patients with extensive burns to determine which factors are predictive of quality of life outcomes, okay? That would kind of fit in where we would use regression. Linear regression is the simplest form of regression, and it simply involves the examination of two variables, x and y, and they are linearly related or correlated, okay? The variable x, or the variable designated as x, is considered the independent or predictor variable, and the variable designated as y is considered the dependent or criterion variable. So let's say we were looking at, I think I did put this example in here. Nope, I didn't. Okay, so let's say we were looking at a systolic blood pressure, Y, and age, X, in a sample of 10 women. We would use a regression analysis. We can use, or using a regression analysis, we can use the data as a basis for predicting a woman's blood pressure by knowing her age. ANOVA is used for analyzing designs with 3 or more conditions or groups that are compared. This is an analysis of variance, so we're looking at variability. The ANOVA is a powerful analytical tool for analyzing designs where, like I said, 3 or more conditions or groups are compared, and it's used to determine if the observed differences among a set of means are greater than what would be expected by chance alone. It is based on what we consider the F statistics, so when you see an F statistic throughout a research article, know that it's related to an ANOVA. And this is similar to a T, that it is like a ratio between groups treatment effects to within groups variability. And the test can be applied to independent groups or repeated measure designs. There are different types of ANOVAs. There's a one-way, there's a two-way. I won't go into great detail, but you will practice calculating your own ANOVA. It's a complex type of statistical tool that we, for the most part, always do in Excel. But it's a very useful parametric tool, and it can be used for multiple classifications. So the sum of squares is, well, we talked a little bit about the sum of squares. So I've mentioned that we established that the mean differences can be evaluated using a statistical ratio that can relate the treatment effect to an experimental error. Okay, how effective was the treatment to was an experimental error involved? The analysis of variance, or ANOVA, uses the same process, except that the ratio has to now account for the relationship among several means. So the F statistic is used to determine how much of the total observed variability in scores can be explained by differences among several treatment means, and how much is attributable to unexplained differences among subjects. And to analyze that variability, we have to use the sum of squares to figure that out.